Thank you for the invitation and letting me speak about basically what I realized as I was putting together this presentation is a description of my work and headaches that basically have every day. Because what I'm going to talk about after the very nice framework that David Zilberman set up is I'm going to concentrate about mitigation and mitigation in agriculture in particular. And as I said, I'm going to try to describe sort of the tools and the questions that we're addressing. And you will see that there are lots of problems in sort of the questions, the methods, and the questions that we're trying to answer. However, I think hopefully it's going to be interesting, and maybe there's some hope for agriculture and mitigation. So first of all, just to set up so the issue, agriculture is thought to be a net emitter of greenhouse gases. It depends on, you might find several numbers in the literature. It depends on if husbandry is accounted for or not. But one of the figures out there, it's 14% of total greenhouse gases, emission of greenhouse gases. The emissions come from fertilizers, and so nitrous dioxide, livestock, and therefore methane, and then rice production, typical irrigated rice production, and so methane again, and then soil mining, and therefore depletion of carbon, soil organic carbon, and emission of CO2, and also land degradation, and also the drying of peat and wetlands in agriculture. This is a map that it's also, you might have seen in the literature. It's sort of trying to geographically assess what is the technical mitigation potential, okay, in agriculture. And what is important here to understand is that, is the word technical. So it doesn't have anything to do with economics, right? It's just that if you could really extract all the potential for mitigation in agriculture, these are the estimates, and I think it's interesting. I mean, it could participate to solving the issue of climate change, and could contribute, and it could become, as opposed to a problem, agriculture could become part of it. So, the way that we think about mitigation in agriculture is that basically farmers should adopt or change, should adopt some agricultural practices or change crop patterns in a way that they could sequester CO2 from the atmosphere and store it in the soil, or reduce greenhouse gas emissions. And obviously, in this, you could also plant trees and store carbon in trees. CO2 sequestration, so carbon sequestration and methane and reduction of methane emissions are considered a little bit easier than the issue of nitrous dioxide. That's mostly due to measurement issues. Okay, so right now the research and the projects and the pilot studies mostly concentrate on carbon sequestration and some reduction of methane emissions. It's a little less about emissions of nitrous dioxide. However, I want to stress that it's extremely important to actually keep in mind that we do a full accounting of greenhouse gases, because if we put in place a system, right, that compensate carbon sequestration, and then we realize 5 years, 10 years from now that yes, you are indeed storing increasing soil organic carbon and storing carbon in your soil, but you increase nitrous dioxide emissions, that could become a problem. It becomes a liability, and so in the market could become. There are lots of issues that could arise from that problem if it's not dealt. If it's not dealt, and it's sort of left untreated. There has been a lot of attention on the issue of carbon mitigation, climate change mitigation, and I think as David was hinting, I think it attracted a lot of attention because particularly for some institutions, there was this hope that it could actually provide some extra income to farmers. It could also address the issue of adaptation, and basically address the area of food security and resilience. So, like a project on which I spent a lot of time working is this partnership that IFPRI has with IFAD, the International Fund for Agricultural Development, and they're particularly interested on the impact of climate change mitigation, particular agriculture and poor farmers. And as I said, their thinking is that there might be an opportunity to take these carbon payments, right, and channel money basically from rich country to developing countries and to poor farmers. And so that is the motivation behind a lot of the actions of international organizations. However, we have to be very, very careful. We have to be careful because, well, you will see during my presentation why there's a lot of uncertainty. And yes, there is a potential to tap into this extra income, this payment for the service that farmers can provide, but there is a lot of uncertainty in this. There's a lot of uncertainty, and we're still dealing in reducing the uncertainty that is involved in the whole setting up the scheme of carbon payments. When I talk about carbon payments, by the way, in reality, I mean any type of mitigation service. So, what are the co-benefits of mitigation? Okay, this is also important. When you mitigate, it's not just that you help solving the problem of climate change, but basically, if you look at the list of practices that are recommended to induce, so for farmers to basically to contribute to mitigation, that list of practices overlap considerably with sustainable land use management. So there is not only you address the problem of climate change mitigation, but you also do something that is environmentally sound. There is a positive correlation between soil organic carbon and crop yield. Okay, any agronomist will tell you that. And some of these are the agricultural practices that are good for climate change mitigation. They are they basically what they do, they increase the amount of carbon in the soil, and so the soil becomes more fertile, and you have high yields. It stabilizes yields, supposedly. There is a more efficient usage of water, and therefore reduction of CO2 emissions that come from pumping water from the ground, and you can sort of change the water management practices in a way that reduces methane emissions in rice. And also, there's also this byproduct that if you were able to put in place a system that provides carbon payments for farmers, there's a whole sort of extension service, knowledge distribution that comes together, and a system in place that could actually provide a lot of support to farmers. So this is also a list of co-benefits that could come from implementing some sort of mitigation project. But there are lots of constraints, right? It hasn't happened yet. And so there is a growing body of literature out there that looks at all the different issues. Here I have listed a few, and I have arbitrarily divided them in 3 areas, just for the sake of this presentation, and then there's overlapping between the areas. But just so that I can move through these issues efficiently, I divided in some sort of biophysical issues, which is defining the baseline and the evidence of additionality. And then there are socioeconomic issues, the cost effectiveness of these payments, dealing with the transaction costs, the property rights. And then there is the issue of leakage and permanence. That I say that it's more like a modeling tool, but actually, probably it moves across all the other 2 areas, biophysical and socioeconomic. By the way, leakage is this issue that you stop deforestation somewhere, right? But it pops up somewhere else because the demand for forest product is still out there. So you prevent the issue in a particular location, but you have exactly the same amount of emission somewhere else, right? And permanence is the problem of making sure that whatever practices you put in place that are good for climate change mitigation, they stay in place for an amount of time that it is considered beneficial for dealing with climate change, right? And so you might have a contracting system, you might have so you enter into issues of monitoring and so on. Let me start with biophysical. So the first thing is to define the baseline, and we have to be very clear when we talk about defining the baseline. It's not like the typical cost-benefit analysis, and so you shouldn't be confused with dealing with sort of determining the initial conditions. It's more like something like this. So when you define the baseline, you have to be able to tell what the carbon profile of the soil will be from here to the next 20 years. Okay? So you have to really be able to map out what either emissions or carbon in the soil is from here in the future. And then you simulate or you sort of account for the adoption of mitigation practices, and then the difference, right, that badly shaded area in that picture, that is the amount sequestered and the amount that would be compensated, right? This is for carbon sequestration, or you can have a reduction of emission, right? But what is important here is the fact that you have to be able to create this baseline, which is a tremendous challenge as you start thinking carefully about it. So, first of all, you have to know how, so in order to sort of understand and simulate and be able to compensate farmers for their practices, you have to be able to translate how much, say, no-till on a particular soil, or the use of manure, or the use of optimal amount of fertilizer translates into a higher amount of carbon or a reduction of emissions, right? So, and you do that, generally what we do, we use a lot of these crop modeling tools that we rely very heavily on those. And so there is the DSAT century model, which is the one that is most widely used at IFPRI, but then there is also CropSys and EPIC and APSIM. They all do sort of different things, and they overlap some, but they also miss very important parts. For instance, except for APSIM, all the other three, they don't deal with intercropping. Well, some areas of the world, it might be fine, but if you think about Africa, well, you're in trouble, right? When you're trying to map out how soil organic carbon is going to develop, and you don't have intercropping, I mean, I feel a little uncomfortable, right? And APSIM does that. The problem is that APSIM doesn't have cassava in the list of crops that you are modeling. So how can you model agriculture in Africa without cassava, right? So these are the deal that, I mean, these are problems we're dealing with. But at any rate, what you have to do, you have to have a tool that allows you to model how using a certain cropping system, using a particular crop in a certain way with a certain rate of fertilizers, water management, and so on, how that corresponds in terms of to emissions and soil organic carbon. Also, in order to create this baseline and also to be able to say how much what kind of difference that makes in terms of emissions or carbon sequestration, you have to be able to reasonably well predict what farmers are gonna do, how they're gonna farm their land, the crop systems they're gonna use from here, say, to 10 years from now, 20 years from now. Then again, if you think about a rice farmer in Vietnam, maybe that's plausible, right? If you think about a farmer in the United States, well, corn, soybean, in Illinois, corn, soybean, corn, soybean, corn, soybean. You have a pretty much set path. But think about the farmers here. I work in Ghana a lot. I work in Mozambique quite a bit. And farmers they're optimizing something, right? They're maximizing some utility function. It's hard to get a hold of that had utility function because if you're planting cassava and I have a new kid, or I'm hungry, or the market is not doing particularly well, I'm going to harvest a little more. So it's hard to really map out what farmers do in a way that we can translate those practices into some sort of carbon profile or emission profile. For instance, the work that we're doing in Ghana, right? We have been trying to assess agricultural mitigation potential in Ghana. So this is just for agriculture. There's no forestry involved. Okay, not even agroforestry. So we took all the provinces, and for each province, okay, we picked the most common cropping systems, rotation cropping systems, and and then we thought about mitigation options, talking with people on the ground, and from their experience we could see what farmers probably could do. This is a little table that describes sort of these cropping systems per province, okay? Now, as you can see, so the Ashanti province, maize, cassava, and 2 years of fallow. Right there you see that, yes, there will be probably a good share of farmers that do that, but there are many, many farmers that maybe have 4 years of fallow, or the rotation is slightly different, right? And also, we couldn't account in our simulation for the fact that not only the typical farmer has maize, cassava, but there's also plantain and there's also cocoyam at the same time in the field, right? So you see, we needed to simplify tremendously to be able to model, to create a model and sort of, and for the problem become treatable, okay? And so, when you do that, then you come up with this. I'm not sure how sort of how much you can see, but basically you can determine these are on the y-axis there are soils that are classified according to their texture, so clay soils, loam soils, and sandy soils. And then if you can make, there's a blue line that is business as usual, and then when you adopt this, certain mitigation practices, you have the orange line that actually gives you the difference, right? And so that difference is what we saw before, the shaded area, that would be the gain in terms of reduction of emissions or carbon sequestration, or whatever it would be compensated if you had a carbon payment scheme. Not surprisingly, the bottom line where you see, so on sandy soils, there's very little sequestration possible. Okay, and then when you have these simulations, you can create maps like this one. So these are carbon sequestration potential in agriculture for Ghana and Mozambique. This is if the farmers in Ghana were to adopt an optimal amount of fertilizers, okay, and in Mozambique fertilizers and no-till, and then you keep going on simulation for the combination of fertilizers and manure applications, and then fertilizer and manure application and residue, some sort of optimal residue management. And you can see that the climate change, the mitigation potential is increasing, and you can start sort of locating where that mitigation potential is higher. Now, I don't have it here, but you can overlap these maps with sort of poverty maps, right? And you can see if that hope of having high potential for mitigation, right, and poor farmers, if that hope is fulfilled, so that you can actually help poor farmers. Well, I can tell you that, as I said, I don't have it here, but that is not exactly what happens. It's more like a middle range, where you see the dark blue, that's where the higher mitigation potential is, and those are not the poorest provinces, okay? That doesn't mean that, whatever payments wouldn't help farmers. Probably they will help them a lot, but you can't really target this stuff to poor farmers, per se, okay? You can't do that. And it's actually, I don't have it here, but it's a little bit of other work that I've done. It shows that poor farmers and that work on poor land in terms of fertility have also very little mitigation potential. So we have to help them using other instruments, not these carbon payments. Also here, just to tell you more about the problem of creating this baseline, I have for some of the simulations that we have been using. Here is simulated cassava and fallow and maize and fallow for a particular location in Ghana. And these are so these lines are how the soil organic carbon develops in the soil through the years. So it goes from 0 to 50 years, which is it's crazy, right? To think about, for a farmer actually to think about what that farmer will do from today to 50 years from now, right? It doesn't make much sense. But what I'm trying to show here is that playing with these models, according to the different baselines that you use, you might have big differences in terms of mitigation potential. So you might have 50 tons, okay? So after 20 years of applying and using the prescribed mitigation practices, you might, according to the different baseline, you might have a difference of 50 tons of CO2 equivalent, or in other cases, 40 tons of CO2 equivalent. This is all to say that the uncertainty is very high. We now have the tools through the crop modeling systems, right? Surveys in the soil, surveys, with farmers, and trying to map what farmers are doing. Where we have the tools, and yet there is quite a bit of uncertainty. Now, it's not just uncertainty that comes from the modeling, the crop modeling. The uncertainty also comes from our the models that predict climate change, right? Because there is a lot of uncertainty in there too. So here I have 4 pictures that basically show different general circulation models. Those are the models that basically show how precipitation is going to change, precipitation temperature is going to change globally. This is the same economic scenario, that A2 over there is the same scenario in terms of emissions, but look at the differences across models in terms of changes in precipitation. Different models, different maps. So as David was saying, is that what we know is that there will be winners and losers. We don't know exactly what those winners and losers are yet. Okay? You might think that yes, there is a migration probably from equator to northern areas or higher latitude, but there's also more complicated stuff that happens at the location, specific location level, and so as I said, there's a lot of uncertainty that we have to deal with, and in fact, if you look at those, if you go back to that sort of carbon sequestration potential profile, the columns there represent different climate change models. And so you get different numbers according to the climate change model. So we have to find a good way of dealing with this uncertainty. Now, why is uncertainty a problem? Well, we know, any agronomist can tell you that, well, if you use certain practices, probably soil organic carbon is going to increase. Well, if you use agroforestry, right, you're going to store some carbon in those trees. And so we know that certain practices and cropping systems will deliver in terms of mitigation, but there's a high level of uncertainty, and we need to, first of all, we need to gather more data to reduce this uncertainty. So there is a lot of groundwork for soil scientists, agronomists to really reduce the uncertainty and to do better in terms of crop modeling. And then there is this problem, what is the level of accuracy in these measurements that, if you wanted to involve the private sector, that it's tolerable for the private sector? Well, the private sector doesn't like uncertainty, right? You don't know how many, if you're willing to pay a certain price for a ton of carbon, but you don't know. You have a plus minus 50%. You're in trouble, right? If you're an investor. What is the level of accuracy necessary for the public sector or international organizations or plans that are developed at the national level? We don't know. These are all sort of questions that need to be answered. But as I said, I guess we will find out. But also at the same time, there has to be some groundwork on the research side to try to reduce this level of uncertainty. And as I said, in order to put in place this system, we need to achieve a certain level of predictability. And this is why, in my work, I'm steering towards, rather than carbon sequestration, towards reduction of emissions. It seems like a safer area rather than carbon sequestration. Carbon sequestration had this problem of measuring the additionality of while instead, when you reduce emissions, that's a net gain. It's right there. And so issues like biochar, alternative to slash and burning, and so they become very, very attractive because you can measure those things very, very nicely. And also slash and burning, for instance, in some areas like Ghana, is something that it's a common practice. You can count on farmers to do it, so you don't get into that trap of having to sort of model cropping systems. Socioeconomic areas. Well, the goals in terms of sort of cost effectiveness depend on sort of the choices and the questions depend on the goals you have. If your goal is to reduce CO2 emissions by a certain amount, you will have to answer certain questions. If the goal is to make agriculture carbon neutral, you have to devise different instruments. At any rate, there is the need for a lot of empirical work. This is I stole this figure from the McKinsey report, and so these are marginal cost curves that the McKinsey basically it's showing, and it shows that different practices, policies have different costs and have a different impact. Now the problem is that McKinsey, I haven't tried myself, but I've been told that it's very difficult to understand, to get from them a little more detail in terms of how they derive this marginal cost curve. But what I'm trying to show here is that there's some basic economic work that needs to be done. And let me show you this picture here. So this is something also it's sort of a simulation that we did for, once again, specific location in Ghana. Basically looks at the profitability of adopting, so when you have a cropping system that is cassava, and actually maize, cassava, and fallow, and then you'll use minimum tillage and chicken manure, okay? This blue curve basically separates two areas. On the left of the blue curve is the area in which, for those applications, okay, you have to provide some sort of payment. To the right, basically, those practices become self-sustainable. So the profit is higher, right, when you adopt those practices than otherwise. So what you see, what is interesting here is that those practices become profitable after a certain number of years. Obviously, they change the soil structure, and so they increase yields, and so they become more profitable. It takes time. So if you have a carbon payment system, the carbon payment system, it doesn't have to stay in place forever, right? It only has to cover some sort of transition, after which you can remove the payment, and farmers will stay on that path. They will keep adopting those practices, which is a nice, interesting thing in terms of the monitoring, right? Because you only have to have the monitoring for a limited amount of time. there's a problem here. First of all, if you see, the blue line intersects the y line, the y-axis, which means that for certain level of manure applications, this model tells us that farmers should do it anyway. They should do it, right? Well, they don't do it, but the model tells us that they do it. They should do it, so it's more profitable. Well, so obviously this idea of looking at farmers and looking at farmers like we did in this case, assuming that they're risk neutral, has problems, right? Risk neutrality, I think it's a very bad assumption here in Africa. And now David can tell us maybe more, because he did a lot of work on risk aversion, and I think it was sort of sexy for economists to work on it, probably a few years ago. But now it seems to me the empirical work in Africa has disappeared on this issue of risk aversion. And instead, let me show you this. So this is the standard deviation of sort of for cassava and maize. Sorry, this gets a little messy, but basically those lines show standard deviation through time for different application rates. And what it shows, okay, is basically that yield variability is increasing for certain rates of application. So if you think that a farmer is risk averse, and you can think of risk aversion being captured by this sort of yield variability, well, you have to factor that in your analysis, okay? And there's plenty of evidence right there out there that shows how farmers are definitely not risk neutral well, maybe in the United States, in Europe they might be risk neutral, but in Africa it's hard to think of them as risk neutral. And David, I have some of your papers here. And so so if you look at the most of the papers out right now that are published, that look at the kind of payments you have to put in place to induce adoption of mitigation practices, they all assume risk neutrality. Wait a second. I mean, that to me strikes. And this is not my area of work. I don't work on. Well, I started now because I see that it needs more research. But my area, it's not really this kind of risk aversion type of analysis. But we did something, just try something simple, and so we took a mean standard deviation utility function, the simplest form, and we tried to simulate some of these things. So once again we use one of these crop modeling tools to model yields and yield variability, and also to keep track of soil organic carbon. And we do this for a time horizon of 20 years, okay? These are details about the simulation. And what you get is that you get different payments. Oh, what a surprise. But, the difference is actually quite high. Now, once again, probably you can make this out of that figure, but you have instances in which once you account for risk aversion, the payments, the necessary payments to induce adoption are lower than under the risk neutrality assumption, and vice versa. It depends on this yield variability, right? So my call here is for everybody to go back and work on the risk aversion issue and try to measure these sort of parameters of risk aversion. So when we use risk neutrality, well, that risk neutrality assumption hides lots of the complexities. And by the way, under risk aversion, you eliminate that really undesirable problem of having adoption, that farmers should adopt those particular practices no matter what, right? You can get rid of that fairly easily just with risk aversion, introducing risk aversion in your analysis. And then there's also the fact that we have to think about the payment, the type of payment schemes that we put in place and the contracting systems. And so there is a discussion, but although this seems to be settled in the literature, that per hectare payments are actually per hectare payment schemes are more inefficient compared to per ton of carbon sequestered. And also this idea of crop modeling, looking at the effect of soils, and including risk aversion, right, shows us that practices, and there are some farmers for which the payment is actually it's lower than in other cases. So there are right practices you can promote and to the right farmers. So we have to have, maybe the solution could be a way of tiering farmers, so selecting farmers that have the highest potential. That's sort of what the Conservation Reserve Program, right, might have. And so we have to think about those tools to be able to select these farmers. And as I said, it goes against this idea that it might help poor farmers, but it helps us thinking about the mitigation potential in agriculture. Then there are other implementation challenges. I'm going to move very fast on this one, that it's really not my area of work, but I wanted to mention because we see how much the institutions and institutional analysis is extremely important if we want to put in place some sort of carbon payment schemes. We need to have institutions that organize farmers and empower farmers with the necessary knowledge, and then the custom monitoring, reporting, and verification. Those are all tied up in these implementation challenges, and it needs a lot of work in for sort of institutional economists. I think I have a lot of a contribution they can make there. And let me conclude with the modeling tools that address leakage and permanence. Okay. So this issue of red, right? Well, first of all, let me say that this idea of separating red, so forestry, from agriculture, to me doesn't make any sense. It really doesn't make any sense whatsoever. Once again, if you want to create, red needs a baseline like agriculture does, right? If you want to know what happens to forestry, you need to know what happens to agriculture. And this idea that the World Bank, it's so stuck up on not considering agriculture, it's just, it's, in my opinion, is not going to lead anywhere. Sorry?
It's not the World Bank.
Well, I was at the World Bank the other day, and I was talking with.
It's a political thing.
It's a political. Okay. So, and particularly with forestry, right? The idea that the historical, you can't just look at the historical data, right? Because the historical data can be very misleading. The case of the Congo Basin and the forest in the Congo Basin, it's a typical example. We see very low rates of deforestation right now, if you look at historically, right? But we have lots of reasons to think that that deforestation will accelerate dramatically in the future. And we also have to think that countries are not, standalone pieces, but they are part of this bigger global economic system. So we need all these pieces together to be able to, once again, to produce a baseline for forestry and agriculture at the country level. So there are. This is now my. I never worked with these models, but David is our specialist, right? GTAP, DREAM, IMPACT. These are all models, either general equilibrium or partial equilibrium, that sort of look at prices and somewhat land, agricultural land, globally. But the problem is that the spatial disaggregation of these models is still very limited. It's not very useful for red implementation and mitigation. So what we need to do is to combine this macro level that these models are capable of reproducing with some more micro, spatially disaggregated models that can capture what happens in one particular location in the global system. This is still missing. Once we have that piece in place, maybe red plus, and we'll make a step forward. I'm heavily involved in this one because this is something we're working on at IFPRI. And so we're using the impact model that we have at IFPRI, and we are combining the work that me, Jerry Nelson, and other people at IFPRI have done on a spatially disaggregated model of land use, and we're trying to combine the two, okay, so that we have this kind of spatial disaggregation, and we can project these changes and disaggregate them spatially. So this is just a picture of how we think we're gonna do it. But in essence, once again, ideally we'll have projections at a pixel level, so at a specific location. This is just one simulation that we have done for the DRC, and right now we're capable of basically projecting prices in the future and also road construction, or the plans that the country has in terms of road construction, and translate that into rates of deforestation. Then at a specific location, then once we have good allometric equations for translating those, what that deforestation means in terms of carbon sequestration, we can see what kind of impact that has for emissions. Concluding, there is potential in agriculture. There's a lot of potential. We don't know how to tap into it yet. Well, we don't know exactly how to do it. We're working hard, but I think so far we haven't had much of a success. There's a lot of need for multidisciplinary work. Soil scientists, crop modeler, economists, and other social scientists need to work together. This is, we need to be able to develop a common language. And it seems to me that particularly for this issue, it's the multidisciplinary work is more necessary than ever. There is a lot of need for data, a lot of work, field work. It's necessary. And yes, indeed, mitigation can be a path towards adaptation, we just need to be able to induce adoption of mitigation measures. And then we have to, as I said the very last few slides, we have to be able to upscale our findings at the farmer level to the macro level. We have to have a system that connects the micro and the macro. Without that, we won't be able to do a good job because, in the end, global warming is a global issue.